Okay, so derivatives of logarithmic functions. Let me give you a moment to copy this example down. Okay, so let's take a look here. All right, we want to find the log, or we want to find the derivative of the log of x to the base a. We want to show that that's going to equal 1 over, and I think I have a typo here, one moment. I have a typo, let me check this. Hang on. One moment. No, we're good. We're good, this is right. Okay. Now, let me ask you, the base A, is the base A, I mean, if we take the log of a base, what does the base A have to be? Does it have to be positive? Or can it be any, can A be any value? Can the base A? All right, base A, that's right, Ian. Base A has to be positive. And what are some like common bases that you've seen? Yes, base 10. That's right, Ian. Base 10, base E. So, you know, when A equals 10, that's called the common logarithm. That's base 10. If A equals E, you're going to have what's called a natural logarithm. Okay, so you should have seen some of that in your pre-calculus. And all right, well, let's go ahead and try to solve. Let's try to show this. Let's show this result here. So we want to show that the derivative of the log of x to the base a equals 1 divided by x times the natural log of a. Now, incidentally, this natural log of a is the same as the log of a to what base? To what base? That's right, Lynn. Very good. Base E. Okay, so, right. That's what that means. The log of a to the base E. All right, well, let's go ahead and proceed. So what I'm going to do first is that y equal the log of x to the base a. Take a moment here. Okay, thank you. I had to ask my brother to close his door there. We like our recordings to be good. All right, so okay, y equals the log of x to the base a. Now, what I'm going to do is I'm going to take a and y and exponentiate it. I mean, I'm going to write a to the yth power. Now, why am I going to do that? Because I already have a rule for taking the derivative of a to the x. Okay, remember, so I had to derive this result, I have to work with results I already know. And the derivative of a to the x power, what's the rule for the derivative of a to the x power? What's the rule? Do you remember the rule for that? That's right, Lynn. That's right. That's right, Ian. Very good. Very good. That equals a to the x power times the log of a. And that rule actually came from section 3.4. Okay, that came from section 3.4. And we're going to make use of that rule to help us derive the log of x to the base a. So, okay, we're going to, so a to the y power would equal a to the log of x to the base a power, because the a and the log function, hold on here, there's, sorry, hold on, right, that's right, because a to the y power, since y is defined as the log of x to the base a to the y power is a to the power log of x to the base a. But a and the log of x to the base a are inverse functions, right? So this is going to give you x. Are we okay with that second statement there? Are there any questions? All right. Well, we have not used this derivative rule yet from section 3.4, but we're about to. Because what I have now, what I know is that a to the yth power would equal x. And so I'm going to differentiate both sides of that equation. That means I differentiate a to the yth power with respect to x on the left, and I differentiate x with respect to x on the right. Now, how are we going to differentiate a to the yth power with respect to x? What type of differentiation are we going to do? Implicit. That's right. That's right. And so on the left, the derivative of a to the yth power would be equal to a to the yth power times the log of a. Now we've used that rule from section 3.4. Times, of course, y prime. So using implicit differentiation, the derivative of a to the yth power with respect to x is a to the yth power times the log of a times the derivative of y with respect to x, which we call y prime. Well, now I know that y prime is going to have to equal 1 over a to the yth power times the log of a. And incidentally, we should always recognize, whenever we divide by a function, we always have to consider, could the function ever equal 0? Could the function ever equal 0? And the answer is no. This function, for our situation, a to the yth power, sorry, one moment. Sorry. So a to the y power is an exponential function. That never equals 0. Okay. And the log of a is the log function. Now, let me just see here. One moment. Hold on just one moment before I proceed on here. Yeah, the log of a would also, hold on here, just one moment. Give me one moment. See, the log of 1 is 0. Okay, the log of 1 is 0. So I'm assuming in this derivation that a cannot equal 1. I'm just looking in the book to see if they do anything about that. One moment. They don't really address it, but let's just say that this is not going to be equal to 0. Okay. So we're going to assume this is not equal to 0. Because in the book, this is what they do. Okay, well then dy dx would equal 1 over x times the log of a, because remember, a to the y power is equal to x. A to the y power is equal to x. And so now we have it. We have our result. The derivative of the log of x to the base a equals 1 over x times the log of a. Right? Are there any questions on that result? Okay, all right. So, like for instance, if you had, let me just see here. One moment. Let me just pull up something here. Yeah, let's say you wanted to find, let's say that you had y equals the log of base 2, okay, times 1 minus 3 to the y equals the log. So this is an example, okay? Let's say you had y equals the log of 1 minus 3x to the base 2. And you want to find y prime. Okay. Well, using the formula, you'd have what? You'd have 1 over what's going to be in the denominator. Something times the log of something, right? Okay. 1 minus 3x, good, would go here. And you'd have the log of times the log of 2. Is that it? Is that the answer? Anything else? I mean, is that our final answer? Ah, Sebastian's right. We have to use the chain rule because we have the 1 minus 3x. So the outer function is the log. I appreciate all the participation. The outer function is the log base 2, but the inner function is 1 minus 3x. So to take the derivative of the log, we used our rule here. But now that's the outer function, but now we got to take the derivative of 1 minus 3x. And so this all has to be multiplied by -3. And so you will get here, one moment. Yeah, you will get -3 divided by 1 minus 3x quantity times the log of 2. So I thought it was good to just, do that example there. Because we're always used to seeing natural logs, right? And logs to other bases are less common, but we can still take the derivatives of log functions that are to different bases instead of like base e. All right, are there any questions? All right, well, let's move on a little bit. Now, why can't you simplify out the denominator? I could write the denominator, Zoe, as log of 2 minus 3x times the log of 2. I could do that. I could write that denominator out a little bit, but it's okay the way it is. All right, great. Are there any other good questions? All right. Well, then let's do. We have this wonderful formula here. Let's do a little bit more with it. Let me go to the next page. And let's see if we can find. Let's see now if we can find a formula for the derivative of the natural log of x. Okay, a formula for the derivative of the natural log of x. Well, the natural log of x, of course, the natural log of x is the same as the log of x to the natural base e. So I can use my formula. I mean, this formula here is good for when a is any base. Okay, so here I'm considering base e. And I'm just going to apply the formula. Okay. And I'm going to get 1 over x. Let me give you a moment to copy that down and think about it. Okay, so now, therefore, the derivative of the natural log of x equals 1 over x. Are there any questions? Any questions at all? Okay. Well, then let's move forward and look at a few examples here. Yeah, it is. It is interesting, Nicholas. It is, and it's. I mean, you're really seeing in calculus here. You're really seeing some beautiful things. I mean, it's like you're gonna. This is a key to a bigger world. A bigger world. Math you're learning. Math opens up doors to bigger worlds, and this is beautiful stuff. All right, any questions before we move on? All right, thank you. All right, well, let's go to an example here. We want to find the derivative. Well, let me give you a moment to copy this example down. Okay, so we want to find the derivative of the log of this fraction, the fraction being x plus 1 divided by the square root of x minus 2. Okay, so all right, so let's look at how we're going to do this. And notice, by the way, this is the natural log. We're taking the derivative of a natural log. Okay. Okay, so, well, of course, we're going to have to apply the chain rule. And we remember, as we just showed it, that the derivative of the natural log the derivative of the natural log of x with respect to x is simply 1 over x. So on this second step here, this second step right here, what rule did I apply? I mean, what rule was applied to get that derivative? Well, indeed, that we used a quotient rule. Okay, quotient rule got used, and the chain rule got used. That's very good, very good. So the derivative, I mean, of my function, I mean, this is maybe a nice way to think about it. If I call this fraction x plus 1 over the square root of x minus 2, if I think of that as f of x, I'm taking the derivative of the log of f of x. Well, that's going to be equal to 1 over f of x times then the derivative of f with respect to x. Sometimes how many find that helpful, that putting in that little f of x function right there as I did? Is that okay? Does anybody find that useful? Okay, Lynn likes it, Chaco likes it. Yeah, a little bit of labeling. Sometimes I agree, labeling's nice and it helps you just kind of keep things straight. And then, so I applied the chain rule, and then to get the derivative of f with respect to x, I'm going to apply the quotient rule. Okay, and so the derivative of x plus 1 is 1. And I multiply that by the denominator, x minus 2 to the half power. And then I subtract the product of the numerator, x plus 1, times the derivative of the, well, it's the product of the numerator and the derivative of the denominator. And that's what I have here. And then, of course, with the quotient rule, the denominator gets squared. Okay, are there any questions at all? All right, well, so now, all right, thank you, Nicholas. So now you have this, in front here, you have this 1 over a fraction. Okay, that's going to just equal the reciprocal of the fraction. Right? That's what that's going to equal. I mean, if you have like 1 divided by a over b, okay, that just equals, and I'm drawing drawing that to separate it. That's just like 1 over 1 divided by a over b. And so fraction divided by a fraction equals fraction on top multiplied by the reciprocal of the fraction on the bottom. So 1 divided by the fraction a over b will simply equal b over a. And that's how how I got the first part of that. That's why 1 over the fraction x plus 1 over x minus 2 to the half equals x minus 2 to the half power divided by x plus 1. And then I'm just doing a little rearranging for the second parentheses here. Now what comes next is we want to simplify this. We want to simplify this. So what I'm going to do is I'm going to take x minus 2 to the half power and distribute it to both terms in the numerator in those parentheses. Well, x minus 2 to the half times x minus 2 to the half is x minus 2 to the first power, because we just add the exponents, right, when the base is the same. So 1 equals a half plus a half. And then x minus 2 to the half times the second term, you're going to get a half times x plus 1 times x minus 2 to the 0th power. The 0th power comes by taking the half power plus negative a half power. Okay, on your you know, x minus 2 to the half times x minus 2 to the negative a half is x minus 2 to the 0th power. Are there any questions on this step here? All right, well, then what we're going to do is just do a little simplifying here. Well, of course, the x minus 2 to the 0th power, that just equals 1, right? That just equals 1. Then says, why don't we have to multiply the, well, indeed in the denominator, I could multiply the x plus 1 times the x minus 2. But you never know, you see. Oh, in the numerator, x minus 2 to the 0th power, this here is just 1. So in a sense, I did multiply it. X plus 1 times 1 is x plus 1. Whoops. No problem. This here is 1. And so are we okay with that step there? And it would make sense to do a little more work on it. You know, it would let me see here. Well, let's simplify this here a little bit. Let's simplify the numerator. May I move to the next page? Are we good? All right. So here's what we had before. The derivative of the log of x plus 1 over the square root of x minus 2 was equal to this expression here that I have, in the blue box. And I'm going to multiply by 2 on the top and the bottom, just so I can remove the half. Okay, so the 2 here, it's distributed. Both of these terms in the numerator. So in the numerator, then, I'll have 2x minus 4 minus the quantity x plus 1. And then I can do a little more reduction. And in the end, my derivative is going to equal x minus 5 over 2 times over the denominator, 2 times x plus 1 times x minus 2. Let me know if you have any questions. Where's the 4 come from? So when I took, all right, John, good question. When I took the 2 here and multiplied it by the x minus 2, maybe I'll put it in black here, this part here, 2 times x minus 2 equals 2x minus 4. Okay, no problem. Okay. Are there any other good questions before we move on? All right, now, you know, we could have done this problem this could be a little easier. Okay. We could have made this problem a little easier for ourselves. Okay. So there's a second method to do this problem, and it's going to take advantage of the fact that we're differentiating the log of a quotient. Okay. What's the, this is just a little side note here. I mean, we didn't use this in this problem, but what's the log of A divided by B equal to? Think about your log rules from pre-calculus. Log of A divided by B. What's the log of a fraction equal to? The log of A, good, Ian, minus the log of B. And if we had rewritten the log of that fraction using this rule, it would have made our lives a little bit easier. And I'll show you on the next page. Okay, so the second method here for doing this problem is to apply that log rule. The log of our fraction. Okay, so the log of our fraction. So this is like, this is A over B. A over B. So the derivative of the log of A over B is the derivative of the log of A minus the log of B. The derivative of the quantity, the log of A minus the log of B. And so what rule can we avoid using by doing this? What rule are we able to avoid using? Quotient rule, that's right, Trevor. So, okay. Yes, I agree, Joe, I agree. Thank you. It's not always nice to get compliments. Hey, Trevor has a lot of friends in the class. That's good. Okay, well, of course, the square root of x minus 2 I'll write as x minus 2 to the half. I don't believe that, Joe. And, we just do a little, math here, taking a few derivatives. Oh, there is one thing. Over here, how did we get from the log of x minus 2 to the half power to 1/2 times the log of x minus 2? How did we get there? Well, if you have the log, of a to the bth power, that's right. That's right, Trevor. The log of a to the bth power is b times the log of a. So whenever you take the log of something raised to a power, you can put the power in front. I'm going to recall this log rule, maybe from their pre-calculus days. You must have seen it. All right, Lynn's seen it, sure. And so, now I'm able to move forward and work through the problem. Of course, the derivative of a sum is the sum of the derivatives. That's what I, have here in this step. So the derivative of the log of x plus 1 is 1 over x plus 1. And the derivative of the log of x plus 2 is, the derivative of the log of x minus 2 is 1 over x minus 2. So that gets me here. And this answer, now WebAssign would accept this answer, but, we really should be able to show that this answer is the same as we did this problem, we just did this problem. So we should get the same answer using this method. And if we combine these two fractions, we will get the same answer. We will. So take a moment to look at that. Are there any questions? All right, Nicholas is comfortable. All right, Lynn's good. All right, well, if we're good, we could probably move on then. Okay, let's get to our next example. Wow, look at this one. All right, take a moment to copy it down. Okay, so well, what do you think? Are you ready to take the derivative of this? Who thinks that's a little bit? There's no log, Ian. There's no log in this one. It's just, well, what's going to be involved in here? The quotient rule. What rules are we going to need to use here? We're going to need to use the quotient rule, the chain rule, product rule, power rule. Wow, a lot of rules there, right? A lot of rules. A lot of rules. So, but yet we could graph this function. We could see that a lot of rules. That's right, John. There's a lot going on in this problem. But what we're going to do to help us is we're going to use something called logarithmic differentiation. Okay. You see, you know how to do implicit differentiation. So with that knowledge, you can use logarithmic differentiation to find the derivative of this very complicated function. So what we do, how does this work? How does this work? Well, what we do is we take the log of our equation. I mean, we're y equals x to the 3/4 power times the square root of x to the squared plus 1, all divided by 3x plus 2 to the 5th power. So instead of taking the derivative of that complicated function, I want to take the derivative of the log of that complicated function, the natural log. I could choose the log of any base, but I'm going to choose the natural log because the derivative of the natural log of x is just 1 over x. It's the simplest case of the derivative of the log rule. So when we do this, okay, look what happens here. You're using your log rules. Okay, so in the numerator, you have the log of a product, right? You have the log of a product here in the numerator. And you learned that if you have log of a times b, there are 3 log rules, and we've already talked about 2 of them. What's the log of a times b? What's the log of a product 2? You remember? Good. Good. Good, Joe. Good, Sebastian. The log of a times b equals the log of a plus the log of b. So, but then we're dividing by 3x plus 2 to the 5th power in the denominator. So now we're going to apply that second rule, that the log of a, hold on here, the log of a over b is equal to the log of a minus the log of b. We use that rule, and then the log of 3x plus 2 to the 5th power here, well, we'll use that later, but we know that the log of a to the bth power is equal to b times log of a. So we have our three wonderful rules. And who would have thought these rules would help us differentiate functions in calculus? But they do. So I apply the rules and I get down to this step. Let me know if you have any questions. It is pretty cool. I agree. Trevor's asking, where did the 2x, the 2 times come from? That's correct. Nicholas is correct. So you have here the square root of x squared plus 1. That's the same as x squared plus 1 to the half power. And so I bring the half power out in front. I apply the third log rule here. And let's see. Ian says, why does the -5 times the log of... Oh, okay. Right. So now we take the derivative of the log of y. And that's going to give you these three terms on the right. And so now, on the left, the derivative of the log of y with respect to x, well, that's just 1 over y times y prime. What did we use to get that on the left? What procedure did we use? What kind of differentiation? The derivative of the log of y with respect to x. What did we have to use to get that answer? In other words, the derivative of the log of y with respect to x is 1 over y times y prime. What was used there? Good, Lynn. Good, John. Implicit differentiation. Boy, you can see how useful that is, right? All right. Well, now I can multiply through by y both sides of this equation. And so y prime will equal 3y over 4x plus x times y over x squared plus 1 minus 15y over 3x plus 2. All right, and are there any questions at all before we go to the next page? I mean, we're not quite done yet because, well, we're just not quite done yet. Y was originally a function of x. Y was a function of that complicated function of x. So our derivative of this function should be able to be written as a function of x. So WebAssign would not accept this answer. What do we have to do what do we have to do to get to the final answer? What do we have to do to get to the final answer? That's right. That's right. Thank you, Nicholas. We have to plug in the original equation for y. So I'll go to the next page. If we're good. I mean, here's what we have. I'll factor the y out, by the way, in our expression here. There's a common factor of y in each term, so I'll factor that y out, which is what I do. And then I replace the y with the complicated function. Well, this is what y is, right? This y was equal to this. Y was equal to that. Y was equal originally to x to the 3/4 power times the square root of x squared plus 1, all divided by 3x plus 2 to the 5th power. All right. And then this would be your final answer right here. We can't do anything more. Nothing's going to simplify or anything like that. Oh, well, you'll have to do that, though, Nicholas. You'll be putting that in WebAssign, but you can, I mean, by the way, you know, class, in WebAssign, when you have to type in complicated expressions, or if they're a little bit complicated, like if you need a subscript or superscript, how many notice that the calc pad pops up on the right? How many have seen that? Sure, Joe's seen it, and John. And you know, the calc pad is designed to help you enter complicated answers. And you know, it's a little effort, but hey, you know, if it allows WebAssign to check your answer to see if you're understanding things and getting the right answer, I think it's worth it. I wish I had WebAssign when I took calculus. And so, how many think this logarithmic differentiation is pretty cool? How many think it's a pretty cool thing? I mean, isn't it kind of amazing? Okay, Lynn, I don't know. Lynn has kind of a interesting face there, maybe a little scary. Frosty. Okay, that's a new. I've heard that term, frosty. That's a term that I'm getting used to. All right, very good, Lynn. Are there any questions?